So I will be discussing video signal analysis. There are three parts of a composite video signal. First is the camera signal, corresponding to the variations of light in the scene. Second would be the synchronizing pulses, or sync, to synchronize the scanning. And then third is the blanking pulses, which makes the retraces invincible. So what is blanking? The composite video signal contained blanking pulses to make the retrace lines invincible by changing the signal amplitude to black when the scanning circuits produce retraces. All picture information is cut off during blanking time. Normally, the retraces are produced within the time of blanking. When the picture is blanked out, before the vertical or horizontal retrace, a pulse of suitable amplitude and duration is added to the video voltage at the correct instant of time. So for horizontal blanking, front porch is a part of the blanking signal which is located before the sync pulse, which is 0.02 Rs wide or 1.27 microseconds. The back porch is a part of the blanking signal which is located after the sync pulse, which is 0.06 R wide or 3.81 microseconds. After the front porch of blanking, horizontal retrace can begin when the sync pulse starts. The flyback or the retrace is definitely blanked out because the sync level is blacker than black. After the retrace to the left edge blanking is still in effect. As a result, the first part of the trace at the left is blanked. After the blank trace time at the left edge, the blanking pulse is removed. The effect of the horizontal blanking is illustrated by the black bars at the left and right sides of the picture. Now, for the vertical blanking, the vertical blanking pulses change the video signal amplitude to black so that the scanning beam is blanked out during vertical retraces. The width of the vertical blanking pulses is ranging from 0.05 volts to 0.08 volts. So if we take 8% as maximum, and since V is equal to 1 over 60 seconds, the vertical blanking time is represented by 0.08 multiplied to 1 over 60 seconds would be equal to 1333 microseconds. When we divide the vertical blanking time by the total line period, would result to 21 lines. Therefore, 21 lines are blanked out in each field and 42 lines are blanked out in one frame. Synchronizing pulses in vertical blanking. The sync pulses inserted in the composite video signal during the wide vertical blanking pulse includes equalizing pulses, vertical sync pulses, and some horizontal sync pulses. So below is the graphical representation of synchronizing pulses in vertical blanking. As seen on the graph, the last four horizontal scanning lines at the bottom of the raster are shown with the required horizontal blanking and sync pulses. Immediately following the last visible line, the video signal is brought to black by the vertical blanking pulse in preparation for a vertical retrace. The vertical blanking period begins with a group of 6 equalizing pulses spaced at half-line intervals. Next is the serrated vertical sync pulse that actually produces vertically flyback in the scanning circuits. The serrations also occur half-line intervals. Therefore, the complete vertical sync pulse is 3-line wide. Following the vertical sync is another group of 6 equalizing pulses and a train of horizontal pulses. During the entire vertical blanking period, no picture information is produced. This is because the signal is blacker than black, so meaning that vertical retrace can be blanked out. The serrated vertical sync pulse forces the vertical deflection circuits to start the flyback. However, the flyback generally does not begin with the start of vertical sync because the sync pulse must build up charge in a capacitor to trigger the scanning. So if we assume that the vertical flyback starts with the leading edge of the third serration, then the time of one line passes during vertical sync before vertical flyback starts. Also, 6 equalizing pulses equal to 3 lines occur before vertical sync. Then 3 added to 1 is equal to 4 lines are blanked at the bottom of the picture just before vertical retrace starts. As the scamming beam retraces from bottom to top of the raster, 5 complete horizontal lines are produced. This vertical retrace can be completed easily within the vertical blanking time, with 4 lines blanked at the bottom before flyback and 5 lines blanked during flyback. 12 lines remain of the total 21 during vertical blanking. These 12 lines are the top of the raster at the start of the vertical trace downward. Therefore, in the total of 2 fields, 8 lines are blanked at the bottom and 24 lines at the top. The scanning lines that are produced during vertical trace but made black by vertical blanking form black bars at the top and bottom of the picture. The height of the picture is slightly reduced with blanking. So a simple video waveform is graphically shown in this slide. So as you can see, there is a black bar that is between the house and the waveform just below it indicates the scanning line. Here are different graphs that shows the odd lines in first vertical trace and inactive lines in first vertical retrace, and even lines in 2D vertical trace and inactive lines in second vertical retrace. So the total for the frame would be equal to 525 lines. So this figure shows the interlaced scanning system. As you can see, there are 2 fields, and the retrace would be the one with the red line that is above the scan line. So as the note states that this representation is not clearly the actual representation. It is only shown so that it would be clear to understand. So the television bandwidth is 6 megahertz. The subcarrier for the color is 3.58 MHz of the carrier for the monochrome information. The sound carrier is 4.5 MHz of the carrier for the monochrome information. There is a gap of 1.25 MHz on the low end and 0.25 MHz on the high end to avoid crosstalk with other channels. Television has a maximum frequency bandwidth of 6 MHz. This says that the highest resolution signal is something like 1/6 MHz or 166.7 nanoseconds. This is consistent with the 330 element scanline with a 8.7 microseconds blanking time. So the lower visual sideband extends only 1.25 MHz below its carrier, with the remainder filtered out. But the upper sideband is transmitted in full. The audio carrier is 4.5 MHz above the picture carrier, with FM sidebands as created by its positive-negative 25 kHz deviation. The lower sideband is mostly removed by filters that occur near the transmitter output. While only one sideband is necessary, it would be impossible to filter out the entire lower sideband without affecting the amplitude and phase of the lower frequencies of the upper sideband and the carrier. Thus, part of the 6 MHz bandwidth is occupied by a vestige of the lower sideband, which is about 0.75 MHz out of 4 MHz. It is therefore commonly referred to as vestigial sideband operation. It offers the added advantage that carrier reinsertion at the receiver is not necessary as in SSB, since the carrier is not attenuated in vestigial sideband.